Good morning, everyone. Myself, Ashu Sharma, Assistant Professor, Department of Computer Science and Engineering, Arya Institute of Engineering Technology and Management. Today's topic for discussion from unit number 1 is basic relationships between pixels. So let's start with our topic. See, as I said earlier, that image is nothing but it's a two-dimensional that array form. So we have this picture which is 2D and having dimension 3 by 3. So original position of pixel that we assume is I comma j. Here we are studying this basic relationship between pixels. So let's be considered this is the origin that I comma j is that is position. Origin starts from here. You can say 0 0, and like that you can further move 0 1 0 2, 1 0 1 1 1 2, 2 1 2 2, 2 0 2 1 2 2. So this is the way you just index it, and we assume this position I comma j. Now we talk about neighbors of pixel small p that we assume in previous slide. So four neighbors, when we talk about four neighbors, so it is the concept that we can say that it is top, this is bottom, this is just left, and this is right. So this is that four neighbors connectivity from this point I comma j. Then we talk about the diagonal neighbors like this diagonal, and then this is I minus 1 comma j minus 1, here I plus 1 j plus 1, here I plus 1 j minus 1, and I minus 1 j plus 1. So it connects all these diagonal elements with respect to this I comma j. Next is 8 neighbors matrix is having this, all these 1, 2, 3, 4, 5, 6, 7, 8. These 8 neighbors that with respect to this I comma j, which is originally we assume that position. So this is the neighborhood connectivity. When we talk about that pixel at its position, we assume that as a central pixel at this point I comma j. Now adjacency and connectivity. Connectivity, two pixels are called connected if their gray levels satisfy a specified coercion of similarities. If their gray levels satisfy the coercion of similarities, then you can say that two pixels are connected to each other. Adjacency, let capital V be the set of gray levels to define adjacency. For example, that binary image V that is equals to 1, and for gray level image B it may more elements like 3, 57 to 55 and so on, because in binary we only have that array value possible is binary, either 0 or 1, but in gray level its range starts from 0 to 255, so any value is possible in the array in that. So when we talk about the array matrix of binary image, it is a binary array, and when we talk about the gray level image matrix, it is numeric array because it starts from 0 to 250. Now the four adjacency, two pixels P and Q with gray values from P are four adjacent. If Q is in N4P, so it align in one of these positions. So you can say that is Q is in 4 neighborhood state, and 8 adjacency, 2 pixels P and Q with gray values from V are 8 adjacent if Q is in this neighborhood and 8P. So these all belongs to that 8 neighborhood connectivity with respect to this I comma j. So that is we have for 8 adjacency. Now for adjacency, mixed adjacency, two pixels P and Q with gray values from V are 4 adjacent if Q is in N4P and Q is in NDP, and that set N4P intersection N4Q has no pixels whose values are from P. So here is an example that modification of 8 adjacency that removes ambiguity that arises when using 8 adjacency. This is the original matrix we have. Now according to this A, arrangement of pixels. So this matrix suggests us about the arrangement of pixels, and B matrix suggests about that pixels that are 8 adjacent. So here we can see this is the dotted line to which we are showing this connectivity with respect to this pixel to this pixel and this pixel like that. So this is in the B, we have pixels that are 8 adjacent showed with this line to the central pixel. and this is the M adjacency. This is the small m mixed adjacency. We have diagonal as well as we have that type of eight, that adjacency is also there. So this is the mixed adjacency where we have multiple adjacencies together among the pixels. Now, M adjacency, mixed adjacency, one of this example is V equals to 1. So we have this binary matrix. All the entries either 0 or it is equals to 1. So find M adjacency between B and C, whether it is there or not. B and C. Yes, that is there. So this is answer yes. So we have certain problem statements that we can identify using this concept. Now more on adjacency. Two image subset S1 and S2 are called adjacent if some pixels in S1 is adjacent to some pixels in S2. So we can say that adjacency, it might happen when two image subset S1 and S2 are called adjacent if some pixels in S1 is adjacent to some pixels in S2. So here adjacents mean, you can say, as we saw, that 4 adjacency matrix, 8 adjacency matrix, and M adjacency, which is mixed adjacency matrix. So here we can see that adjacency that happen over here between these pixels. We take this as a separate into two parts, S1 and S2, and these are called adjacent if some of these pixels are adjacent to pixels of S2. So here is a question like that. So we have to find out what type of adjacency among the pixels between S1 and S2. This is very, very important concept when we talk about that. Now, there is something which is path and curve. A digital path oblique curve from pixels P with coordinates x comma y to pixels Q with coordinates s comma t is a sequence of distinct pixels with coordinates x0, y0, x1, y1, xn, y. So basically, we can say a digital path of curve from pixel P with having coordinates at a spatial position x comma y to pixel Q with coordinates s comma t is a sequence of distinct pixels with coordinates that starts from x0, y0, x1, y1, xn, y1. So all these are the intermediate points in between x comma y and s comma t, which is starting and ending pixels coordinates. So where x0, y0 equals to xy, let's we assume that the starting pixel having x comma y and xn, yn we assume s comma t, and the pixels xi, yi and xi1, yi minus 1. It means this is starting from the second and this is ending last elements, ending from the second last elements are adjacent for in between I is equals to 1 to n. So it ranges from I1 to n, where n is the length of the path. When we say about the closed path, it means initial and start that position. So x0, y0 equals to x and yn. Then we say it's a closed path. Path can be again we can say it's a 4 path, it's a 8 path, or m path, depending on the types of that adjacency we have. So this is there. Now the connected component and connected set. What are those? Let S be the subset of pixels in an image. Two pixels P and Q are said to be connected in S if there exists a path between them consisting entirely of pixels in S. So S be the subset of the pixels in an image, and we consider 2 points P and Q are said to be connected in S if there exists a path between them consisting entirely of pixels in S. For any pixel P in S, the set of pixels that are connected to it in S is called connected component of S. And if it has only one connected component, then S is called a connected set. So if I brief this concept that two pixels P and Q are said to be connected in S, which is a subset of pixels in an image, if there exists a path, there should be a path between them consisting entirely of pixels in S. So if there is a path between P and Q, so you can say, okay, that is connected. For any pixel P in S, now we take any pixel P in S and the set of pixels that are connected to it in S. So how many pixels are connected to pixel P in capital S, which is a subset of pixels in an image? That is considered as connected component of And if it has only one connected component, then set S is called a connected set. So if we say, okay, it has only one connected component, then the set S is called the connected set. Now, region and boundary. Let R be a subset of pixels in an image. R is called a region if R is a connected set. So there should be a connected component over there. So we can say that we put it into the connected set category and we say it is R is a region. It may be interior or it may be exterior region. Now the boundary border contour of R is the set of pixels in the region that have one more neighbors that are not in R. So we can say boundary that separates one region to other regions. You can say border as well, and contour of R is the set of pixels in the region that have one or more neighbors that are not in capital R, which is not the part of the R. These are some other regions that is separated by boundary. If capital R represents entire image, then boundary is defined as a set of pixels in the first and last row and column of the image. So that is we have for region and boundary. Now linear and non-linear operations. Let H be an operator whose input and output are images. H is a linear if for any two images small f and g and any two scalar a and b having this expression, this equality, capital H of AF plus BG that is equal to A of HF and B of HG. So B into HG and A into HF. When you take summation of this, it becomes this H of AF plus BG. Result of applying a linear operator to the sum of two images multiplied by constant. So here is a sum. We are taking sum of two images, HF and HG, and multiplying by two constants, two scalar values, A and B, is identical to applying the operator to image individually, multiplying the result by appropriate constant, and then adding these results. So we are multiplying this scalar with this image, multiplying this scalar with this image, then we are adding this. When we talk about the linear characteristics of this operator H, and otherwise operator is non-linear. So let us we just brief this. What we saw four connectivity, eight connectivity, and adjacency, mixed adjacency connectivity. Then we saw connected component, connected set, and we saw regions and the linear and non-linear nature of that H operator. So this is the basic that concept that we cover in this session of the basic relationship between the pixels. Thank you very much for being with us for this session.